First thing we got to talk about is these terms. So you guys have this in your notes, and it is very much like a definitions list, but I want to just make sure we get a little bit of cartoons in here to make sure that we make some sense of this. And I think in the kinematics unit, I had you keep a terms list on the cover page. There's still a terms list on the cover page of this unit as well, but I just needed to have these details hashed out so that everybody has like fully fleshed out terms list. When we talk about air resistance, I mean, oftentimes we're talking about things like a ball flying through the air or something like that. So, it might be something like, this baseball flying through space. But as a baseball goes through the air, you know that it might end up having a velocity going this direction. But if there's a velocity going that direction, what direction would the force due to air resistance be pointing in? Yep.
The opposite.
The opposite, yeah. And so this is something we kind of implicitly know. Sometimes we'll call this force of air. Sometimes, what's the D word that people think of? The resisting force due to air. Yeah? Drag, yeah. So I don't know if you can see this, but if I write the word drag there, force due to drag. And one thing I also want to draw attention to is whenever I do a force diagram, there's a name for them. They're called free body diagrams. And these force diagrams, these free body diagrams, you notice that the velocity didn't get attached to the object. Only the force gets attached to the object. You can illustrate the velocity if you want to as like an off to the side little vector, but it's not allowed to touch the diagram. Okay, so that's a rule. And it's not just my rule, it's a general physics rule, okay? And I was actually just talking with a young man in the hallway just now, came back to visit from Waterloo, and he says, yes, very much, it's the same thing. So, whether you're here in this classroom or whether you're doing your first year engineering at Waterloo, same rules, okay? So just so you know, I'm very consistent, want to make sure that we're setting everybody up for success. But we could say, hey, people use variable f subscript air, or they use, it looks like my marker's going to die, so I'll set that off to the side, grab myself a fresh one, f subscript drag force. And you can read the definition there, the description, but I feel like I've kind of talked about it. The next one, an applied force. Now, an applied force is really just a general term for a contact force. So here I have like a toy car in front of me, and when I push it from behind, I could say that that's an applied force. So it's not any special, specific thing. It's just a term that we use as sort of a catch-all. And so sometimes you'll see F subscript A, sometimes you'll see F subscript APP for applied, but it's just that catch-all force that you apply to something. You exert it on another thing. Buoyancy force. Now, I'm going to sort of blur the lines a little bit. This is a little bit of an illustration. An illustration, as opposed to a true free body diagram, an illustration includes details about the environment, about the setup, whatever. And so if I say that I have a ball that's floating on water, that's an illustration. It's not a good illustration, but it's an illustration. It's not a true free body diagram. A true free body diagram would just have the ball with no extraneous information, and it would talk about what all the forces are that are acting on that ball. In this case, a ball that's floating would have buoyancy force pointing in what direction? Up. Everybody say up? All right, you can shout it out too, it's okay. Okay, so we could say F, and sometimes you'll see just FB for buoyancy, but to write BOUY for buoy is also acceptable. Now, if it was just the buoyancy force acting upwards on this thing, it would blast off into space. So what are we missing? Gravity, yeah. So I'll just write it as FG for gravity, force due to gravity. And of course, all these forces, something because my space doesn't allow, I've made things very small here. It's pretty tight. Are they scalars or vectors? Yeah? They're vectors. How do you know they're vectors without being told? Yeah, they got directions. So if I wanted to be really committed to the cause, I could go back in here and I could add a little vector hat on top of each of those guys. Now you'll notice that I'm going to drop that, but just for the purposes of bringing it up that it is a vector, I've just done it, okay? So that's just for conversation's sake that I've thrown that in there. And that buoyancy force is that upwards force that keeps something afloat because of density differences, really, right? ball. This ball actually probably wouldn't float very well, but I don't know. I have a foam ball here that I won at a science conference by, I'm gonna brag, by knowing how to do projectiles. I was at a physics teacher conference and I was the fastest one to calculate the distance, blah, blah, blah. I got a foam ball. That's my bragging rights, okay? Anyway, it's very branded. It's very product placement. Check out Gizmos. They're awesome. Anyway, but this foam ball would definitely float better. It would have more buoyancy force because the density difference between foam and water is greater. It's a greater density difference. Also why helium floats really well, because it's got a big density difference between helium and sort of the surrounding air. This next one, friction. This is one that people mess up a little bit. Static friction versus kinetic friction. And I'm going to choose a different object. I've got an eraser here. Obviously, if I push on this eraser, you can't tell that I'm pushing on this eraser right now because it's not doing what? It's not moving. Yeah, it's not sliding. In fact, I got to push a certain amount before it actually will slide, right? And the amount of force that I had to overcome to get it to slide is called the static friction force. The amount of force that I experience as a resistance when I actually get it sliding, that's called kinetic friction force. And they're not the same thing. And we'll do like a whole lesson just on those two things. But for now, I just need you to know that static friction force is the resistance force up until the point that it does slide, and the kinetic friction force is after it does slide. Now, at the same time, this is important for shoes. Can you imagine if this is a shoe, rubber sole, and you're walking and you press on the ground? You can imagine you press on the ground and you push off to make yourself propelled forward. Between your shoe and the ground, is it static friction or kinetic friction that makes you go forward? It is. It's static because your shoes don't spin out from underneath of you, right? They don't slide. Unless, in the absence of like a Michael Jackson moonwalk or something like that, your shoes are not sliding. They're like actually gripping, not sliding, and propelling you forward. What about cars? I take this car here and I put it sideways and I say, hey, this car is going to drive on that horizontal line. That horizontal line is the road. With a drive system, isn't this the same as with the shoe? The car moves 100%, but does it slide? No, it's a constant grip and non-slip. Yeah, it could skid. It's true. In icy conditions, it could skid. Absolutely. And that would be a scary situation. But in most controlled situations, we want to make sure that our cars drive using static friction. And the reason I draw attention to that is that sometimes people get mixed up. They say, oh, static friction, that's when it's not moving. Nah, honey. That's when it's not sliding. That's an important difference, okay? With sleds, with toboggans, not moving and not sliding is the same thing, right? With cars, we're talking about it gripping and not slipping. That's really important for cars, right? So it's not moving, it's not sliding. Really important differentiation, which is why I bring it up. And people get confused otherwise. Anyway, one thing I will say here without going into any more detail, because like I said, we're going to do a whole lesson on this, is that the static friction force, Fs, is always greater than the Fk value. Turns out the amount of force it takes to get something going is always greater than the amount of force it takes to keep it sliding. And I also want to make a little correction here based on what I just said. A force that acts in opposition to the direction of an object's, how could I phrase this other than saying motion? Because I brought up this idea of car. What else? What could I say instead of just motion? What if I brought up the idea of an object's slide across a surface? Okay, it's important to recognize that it has to be a slide. Rolls don't count. The normal force. I think I want to read the definition of this one first. It says the force that one object exerts on another, it acts perpendicular to the surfaces in contact. And it's whenever two objects are touching. But most of the time when people talk about normal forces, now truly this is an illustration because I'm drawing a horizontal surface, not just the object, but this is just a box. Just a little box sitting on the ground. When people talk about normal forces, they'll often talk about, okay, well, there's a force due to gravity acting down on this thing. And the normal force, it says that it's perpendicular to the surface in contact. So this is, if this was a box sitting on the ground, the normal force would be pushing up on that object such that the force itself is perpendicular with the ground. And everybody's like, yeah, that kind of makes sense. You know, like here I've got a stack of Post-it notes. It seems to me that when I put those Post-it notes there must be a force that's acting out of the page, you know, out of the screen at you. And there must be force due to gravity pulling those Post-it notes into the desk, you know, away from you. That makes total sense. And it would make sense that the normal force would be perpendicular to the desk that I'm writing on right now. Cool? What about this? It doesn't take a lot to mess with this thing. Yeah, if I do an inclined plane, if I do a ramp, nobody ever argues about this. They say, well, gravity's still going to be down. But according to our definition, what direction is the normal force? Can you guys point with your fingers? Everybody point with your fingers. What's the direction of the normal force? Yeah, well, let the record show everybody says it like this, right? They did it in kind of like a 1970s disco move. And people say, okay, well, according to this definition, that means that vector isn't opposite to gravity. It's perpendicular to the inclined plane. You see the difference? It's not an opposite to gravity thing. It's perpendicular to the inclined plane. In fact, if I were to go and get myself a fridge magnet, and again, we could go grab a fridge magnet. I'm not going to because I can't fit it onto the camera nicely, but also we can just imagine fridge magnets. And I have magnets up on my whiteboard here. You can see what I'm talking about, or you can visit your fridge at home. But if I have a fridge magnet attached to the side of a fridge, gravity, we all know, is this way. What direction is the normal force? Yeah? To the left, yeah. Going to be this way. Now, assuming that this magnet doesn't fall, what direction, or what's keeping it from falling? And don't say magnet. It's actually an F word, and it rhymes with diction. Friction. Yeah. It turns out that if you stick a magnet onto a greased up fridge, it'll have a real hard time sticking. You could try it if you want to. Take some olive oil and stick a magnet to a fridge. Your parents will probably not be impressed. But especially if you have like one of those nice stainless steel ones, right? All greasy. Anyway, that friction force is what's keeping it from sliding down. The magnet is causing there to be a pressure force between the magnetic surface and the fridge, and that causes there to be extra pressure between the two, and that's what's going to cause the surfaces to interact and result in friction. So yeah, look, there's going to be friction, and hopefully if it doesn't slide down your fridge, static friction. And I think we've all been in that situation. If you've ever played around with fridge magnets, you know, you put your physics test up on the fridge because you're so proud of your mark, you're so excited, or maybe it's something else, I don't know, and you stick it up there and there's too many pieces of paper and the magnetic force isn't enough to create enough normal force, and then your test slowly slides down the fridge. You ever seen that kind of thing? Right? So like we know that somehow there must be friction at play here, but maybe we don't always think it out. And this is another thing in physics where we're thinking out the nitty-gritty details of the world that is all around us all the time, right? So I mean, even if you never thought about the thing that's holding your great test up being friction, working in concert with a magnet, you just didn't think about it. You just thought, oh, magnets are magic, right? Like I remember putting magnets underneath of a table and flipping coins and stuff like that above the table. You ever play with magnets that way and you feel like you're doing like a little magic trick or something? That's cool. But they're not magic. Magnets are just drawing or causing an attraction between surfaces, and that attraction between surfaces is causing an increased normal force, and that increased normal force is creating a friction force. And if you lubricate the surface, or if you weaken the normal force, the things are going to slide down. And that's the sort of nitty-gritty thinking we want to get into. Anyway, springs. This is something, again, maybe you never thought about before. But if I have an object and I hang it off of a spring, you can imagine if the spring starts off at this length and I dangle an object off of that spring, can you see that spring I just drew there is stretched now? If this is the original spring, this is the spring with a mass hanging off of it. what direction is gravity going to act on that object? Yeah, that's going to be down. No doubt about it. What direction is the spring force going to be on that object? Up. Yeah, that makes sense. So again, this is stuff that you know. We're just thinking through the details of the world. And if that object sits there at a steady height, it doesn't bounce, it just hangs there from a spring. You know, I happen to usually keep a spring above my head. Can you imagine I hang a mass off the spring that's above my head right now, and it just sits there at a constant height? What would you say about the spring force and the gravity force? What would you say about their strengths relative to each other? Yeah? Yeah, they'd be equal, but maybe opposing directions, but equal, right? Yeah. And so again, that's the kind of thing we're thinking about. We're thinking about what must be the case. If it's just sitting there, the spring force and the gravitational force must kind of balance each other out. By the way, there's a name for that. It's called equilibrium. But we'll get to that, okay? Then we say, hey, what if I take the same spring? You ever taken like a spring inside of an old pen, like a Bic pen or something, and you compress it? You ever try to squeeze the spring? You know, and try to keep it from springing out sideways? But if you were to stack an object on top of a spring, so that originally the spring was this tall, but then I put a mass on top of it, and it gets compressed to being only this tall, what direction is gravity acting on the object? Still down, right? What direction is the spring force acting on? Up, yeah. Leo's got it. Somebody else is telling me too. But again, wouldn't that, I use that big E word, equilibrium. Wouldn't that be an equilibrium as well if it's just sitting there? And this is the kind of thing, this is the kind of physics that goes into the launching of a marble. You ever play pinball? Have you ever played a pinball machine? It's a fun game if you never played it. Maybe not worth all the quarters, but like, you know, it's just like a silly game. And if you pull back the launcher for the pinball, this is what you're doing. You're applying a force to compress a spring, and that spring wants to get longer again. And we'll talk more about springs and their tendencies to get longer at a later date. Now, in terms of the variables, I've been using Fs. You notice that Fs also gets used for static friction. And so in a situation where there's friction as well, oftentimes you'll see people using E for elastic force. Okay, so I know that seems like, oh, that's confusing, but it's just situationally appropriate, right? Because you don't really want to write the whole word spring, because I think we're all lazy. We're just going to write S when it's easy. If you always want to write E, you can. But then there also are times when F lowercase e could mean electrostatic force. So I mean, it's all situational. Okay, so we just roll with it, you know. There's this other one called tension, and I think a lot of us have dealt with tension in our lives, which is a big source of stress. But if I have an object, and I take, and again, this is not a free body diagram, this is an illustration. I got this little stick person here, and they've got a rope, and they're sliding the object across the surface. I don't know what's going on with my stick person art these days, but they're walking, they're sliding this rope. You can imagine that if I take this illustration and I do a free body diagram, remove the human, remove the floor, I could say, well, what direction would kinetic friction be acting on the box? Left or right? Kinetic friction, if I slide this box along the floor, what direction would the kinetic friction be acting? Left or right? This is left. This is right. What direction is the friction acting? Left is the answer. Left is the answer. The friction's going to be resisting your motion. So I could say, okay, Fk is going that way, acting on that box. And what direction would the tension be acting on the box? Left or right? To the right, yeah. Ft for tension. Now take a look at the definition. It says it's a force that's exerted by a string. Now, you know, I can even say through a string. String, rope, or cable on an object that's pulling on it. And this idea of having tension, tautness, tight rope causing a force. You can't have a force exerted through tension with slack. When there's no tightness, tautness, No, if you can't imagine plucking it like a guitar string, you can't exert attention. Lift force. Lift force is something where maybe I want to start off with another illustration. And I think I'm going to choose just like something really simple to draw. Make it like a nice, simple airplane. Single-seater airplane. Okay. Take art. I love art. Stick people airplanes. That's my bag. All right. One time I was in an airplane going over the rainforest in South America. And I remember the guy that I was with, he wanted to insist, is this a 2-engine airplane or a 1-engine airplane? And he was so insistent that we get a 2-engine airplane, and there just wasn't one available. We only got a 1-engine airplane. He was so scared the whole trip. He insisted he sat with the pilot the whole time because he was afraid. And eventually Miss Killens kicked him out of the co-pilot seat so that my son could sit there. Because it's like, let the little boy have some adventure. You're like a 50-year-old man. But anyway, if you can, get yourself a 2-engine airplane if you're ever going over the jungle. That's important stuff. I had no idea. Anyway, we got this jet, and as it's flying, I wasn't in a jet. I was in an airplane. Things that we talked about so far are drag. So we got drag going back this way. What's a force from above on our list that would propel this plane forward? What's one that we could throw in as our propulsion force? It's not drag. An applied force? Sure. Yeah, remember we said applied force is a nice catch-all term? Now, if you're into aeronautics, you might have called it a thrust force. Thrust force is what the jet and plane people might call it. So that's a specific term that's specific to that situation. We're going to call it an applied force, okay, because it's a nice catch-all. If you said thrust, it would have been fine. I'll even label that in. Thrust is a reasonable thing, and that shows up in problems sometimes. The thrust force is so many newtons, and you'd have to roll with it and recognize that they mean it's an applied force. All right. What about in the vertical? Yeah. Gravity, yeah, we shouldn't forget gravity. And here I am on item number 8 in my checklist. What do you think the upwards force is called? Lift, yeah. Now, lift is going to be achieved by the shape of the wings themselves and the flaps in combination. And if you really want to look into that, it's not actually part of this course, but Bernoulli's principle is what causes lift, and you can definitely look that up. It has to do with the relative speeds of air above the wing and below the wing, causing there to be a pressure difference between the two. It actually causes the plane to lift up. But we're just going to call it lift force, okay? So this plane lifts up. It's a force exerted that keeps something in the air and causes it to lift off the ground. Now, if I were going to do a true free body diagram, remember I said this is an illustration, not a true free body diagram. I'll say this, a free body diagram. I've said it out loud, but I'll put it in writing. And it's so common to talk about free body diagrams that an FBD is what almost everybody calls it, just because it's shorter, okay? But a free body diagram for a jet might look like this. You notice that this looks nothing like a jet. It's just a geometric shape. Our FBDs will always just be geometric shapes. They're not intended to be illustrative. Doesn't matter how artistic you are. It's not important. It's just illustrative for keeping track of forces. In fact, you're not supposed to make it look like a jet. You're supposed to just make it look like a geometric shape that represents a jet. Okay? How abstract. And I could say, hey, I got my FG. I've got my F lift. I want to change my diagram that I just drew just a little bit. And maybe I'll even call it thrust force this time. I should even give myself a reference frame. Oh man, because these are vectors, I need reference frame. Up, down, and I don't know, forward, backwards, yeah. Forward, backward. We always should give ourselves a reference frame, positive, negative. But if I was going to talk about this, what's this jet doing? Tell me about its height. Is it going up or is it going down? Can you tell? Tell me about the lift force and the gravitational force. Are they the same or opposite? Or sorry, the same or different? Don't they look like they're about the same? Now, I can't actually tell, and be honest, I can't tell if this thing's going up or down. What I can tell is that the net force, hear that word net force, in the y direction is 0. If the net force in the y direction is 0, that doesn't mean it's not going up or down. What it does mean is it's not getting faster going up or faster going down. So all I can really say is that if the net force is 0, the acceleration is 0. It could be drifting upwards at a constant rate. It could be coming downwards at a constant rate. But it's not accelerating up or down. What about in the horizontal? Is it speeding up, slowing down, going at a constant speed, or going backwards? What do you think is the most likely thing for a jet? Is it speeding up? No. Is it going at a constant speed? No. So then we're left with the options if this was a multiple choice. Is it slowing down or going backwards? Slowing down. Doesn't that seem like the most likely thing? And so this would be what we call an unbalanced force. And an unbalanced force, you got to think about what are the options. The options are this jet's going backwards because the drag force is bigger than the forward thrust. Here's a question though. Can drag actually actively push you backwards like this? Think about it. If you've ever stuck your hand out the window of a rolled down car window, does it push the car backwards or slow the car down? Slows it down, right? Slows the car down. Does not. You couldn't, if you were in a parked car and you stuck your hand out the window, are you going to propel your car backwards? No. So I want to put this out there. The drag force, in the absence of using drag force as a sail, right? In the absence of using it like a sail, drag force is not going to be an active force that's going to push us along, right? It's going to only act to slow us down. Anyway, we could say this is a jet slowing down. If I was going to tell the story. A jet slowing down. I do want to list out a few rules for free body diagrams because I wanted to make sure we could tell a story about this free body diagram, but I also want to make sure that we know how to draw them properly. So a few rules for FBDs. Rule number 1, forces are always drawn acting on the center of mass. And if you go back and you look at the previous drawings that I did here, you notice I was pretty good about having the forces acting on the center of mass. There's a couple times I slipped up because I was trying to be illustrative, but really they should always be acting on the center of mass. Rule number 2, the FBD is a simple shape. Simple geometric shape. And does not look like an object that it represents. Yeah, unless it's a box. I got Alice in Wonderland getting in the way here. Give myself good advice, but I very seldom follow it. So let's just make sure that we do follow these 3 rules of advice, okay? One more. I couldn't fit it in because of my layout. A reference frame is always needed. Okay. I got 3 more forces that I want to take a look at. Just on the next page there. Take this away. Not 3, sorry, 4. And these forces are the forces that people typically call the fundamental forces. And I'm perfectly open to upcoming scientific developments, breaking these down and finding even more fundamental forces than these. But classically speaking, these are the things we call fundamentals. Okay, so it could be that we unlock Pandora's box of physics and figure out that there's even more basic stuff than this. But for now, gravitational force is considered a fundamental force. And what we've been talking about on the previous page is force due to gravity. Oh, look, here's a little illustrative FBD, being a force that acts downwards on something. I'm going to omit the normal force right now because I just want to focus on the idea of gravity. But, on a more cosmic scale, people talk about like the moon orbiting around the Earth. And they talk about there being, if we call this guy the moon, and this guy the Earth. They talk about having a mutual force of attraction between these two objects. And it's that mutual force of attraction that keeps them locked together. And really, they're both experiencing gravitational attraction to each other. It's a mutual attraction. And so whether we're talking about objects near the surface of the Earth or celestial bodies, it's because of how much, how much of what has to be present to cause gravitational force to increase. What are we looking at? What's the root cause of gravity? It starts with an M. Mass, yeah. So we're talking about mass being a thing that causes this. Recently there's been people exploring the idea of the concept of gravitons more and more. And so if you're somebody who likes to go down the rabbit hole of YouTube and look up cool things, like gravitons is a thing that has to be transmitted, kind of like photons, but to make gravity work, this is something that might really get you excited. But it's a fundamental force. Now, electromagnetic force kind of gets put under one umbrella because electrostatic force, which you may have talked about in grade 9, where E stands for electric, and magnetic force, now this is the thing that'll annoy a lot of people. We actually use B to represent magnetic. Well, first of all, English is not the only language. But I also can't remember off the top of my head why we use B instead of M. I think because M was already taken by mass. Okay, so electrostatic force, magnetic force. F subscript E, F subscript B. And I'm not going to spend time on the causes for those forces. We're just hashing out the variables for this one. And then strong nuclear force. That's that force that holds protons and neutrons together within an atom's nucleus. And it really only operates, as far as we can tell, over very short ranges. So this is something that's going to be talked about more in chemistry class, really, than in our class right now. Although we could have a nuclear physics topic, but in our grade right now, we're going to let that be the domain of chemistry. And so the strong nuclear force holds these particles together. And then there's the weak nuclear force that is responsible for the interaction between elementary particles. And if you haven't talked about strong and weak nuclear forces, you will and can, don't worry. For now, we're going to just say, let chem and nuclear physics do this one. We're going to touch on the top two, but we'll let somebody else talk about the bottom two, okay?